What if the universe has placed an object exactly where our categories begin to fail too heavy to be an ordinary neutron star, yet too light to be an ordinary black hole tonight? We follow the strange signal of GW190814, a gravitational wave event that revealed a compact companion sitting on the quiet edge between matter's last resistance and gravity's final silence. It may have been one of the heaviest neutron stars ever hinted at, or one of the smallest black holes nature has found a way to make. Either answer changes the story of how stars die. Before we begin, please take a moment to like, subscribe, and share this video if calm science journeys like this help you relax, think, or drift into sleep. Thank you for spending your time here, and wherever you are, what time is it as you're watching or listening? Leave a comment and let us know. Now, let's move gently into the strange boundary between neutron stars and black holes. GW190814 enters the record as a signal before it becomes a category problem. It is not seen as a bright object against a dark sky, and it does not arrive with the familiar shape of a star, a galaxy, or an explosion spreading through space. It arrives as a passing distortion, a slight change in distance inside instruments built to notice when spacetime itself has been stretched and squeezed. From that quiet disturbance, a physical story begins to take shape. Two compact objects had been locked in a final spiral. One was massive enough to be recognized as a black hole without much hesitation. The other was much smaller, but not small in any ordinary sense. It carried about 2.6 times the mass of the Sun, packed into a body so compact that ordinary categories began to strain around it. That mass sits in a difficult place. It is heavier than the neutron stars most securely measured, yet lighter than the black holes commonly found in stellar systems. It does not fall neatly into the known population on either side. It stands near the boundary where the pressure inside matter may fail, where a surface may disappear, and where the last distinction between a star and a hole becomes a question of physics under its harshest conditions. The event is important not because it is loud, but because it is precise enough to be uncomfortable. Gravitational waves do not bring colour, heat, or shape in the usual astronomical way. They bring motion translated into geometry. The waveform carries the rhythm of orbiting masses as they tighten, accelerate, and finally merge. The pattern is brief, but it is not empty. It contains the imprint of mass, distance, spin, and the balance between the two bodies. In this case, that balance was uneven. The heavier body was roughly 9 times more massive than its companion, creating an asymmetry unlike the first black hole mergers that opened gravitational wave astronomy. The smaller object was drawn inward by an immense partner, circling faster as energy escaped in the form of ripples moving outward at the speed of light. By the time the signal passed Earth, the collision had already become an ancient fact, carried across a vast distance in a form almost too subtle for ordinary imagination. What reached the detectors was not debris or flame, but information in the curvature of space-time. The surprising part lay in the smaller mass. A neutron star is already close to collapse by its nature. It is the remnant left behind when the core of a massive star can no longer support itself through nuclear burning, and gravity compresses what remains into a state far beyond ordinary matter. Protons and electrons are forced together, neutrons dominate, and a mass greater than the Sun may be enclosed within a sphere no wider than a city. Such an object has a surface, but that surface belongs to an environment almost outside daily intuition. Gravity is so strong that escape requires a large fraction of light speed. Matter there is not merely dense, it is pressed into forms that can only be described through nuclear physics, quantum rules, and the balancing act between pressure and collapse. Yet even a neutron star has a limit. Add too much mass, and no pressure remains sufficient. The star can no longer hold itself apart from its own gravity. The surface falls inward past the point from which light cannot escape, and the object becomes a black hole. The difficulty is that the exact mass of that limit is not known with complete certainty. It depends on the equation of state, the relationship between density and pressure inside matter that has been crushed beyond anything reproducible in a laboratory. A softer form of dense matter gives way earlier, allowing neutron stars to collapse at lower masses. A stiffer form can hold more weight before failure. Observations of pulsars, which are rotating neutron stars whose beams sweep across Earth like cosmic lighthouses, have shown neutron stars above 2 solar masses. That alone already demands matter strong enough to resist tremendous compression. But 2.6 solar masses pushes the question much farther. If the smaller body in GW 190814 was a neutron star, then it belonged very close to the maximum nature permits. It would be an object at the last edge of stability, a star only barely avoiding the transition into a black hole. That possibility makes the event valuable even without light. A neutron star of that mass would act as evidence about the behavior of matter in its deepest layers. It would say that dense matter can remain supportive under more extreme conditions than some models allow. It would narrow the range of possible interiors, changing what can be said about the hidden core where neutrons may no longer remain simple neutrons and where more exotic states may appear. But the other possibility is no less strange. If the smaller object was a black hole, then it was unusually light for a black hole formed from ordinary stellar death. Known black holes in X-ray binaries, where a compact object pulls gas from a companion star, have usually appeared at several solar masses and above. The reason is tied to how massive stars collapse. When a core forms a neutron star, an explosion may drive away much of the surrounding material. When collapse continues into a black hole, more material can fall inward, increasing the final mass. This tends to leave a gap between the heaviest neutron stars and the lightest black holes. The gap is not an absolute law, but it has been a persistent pattern in observations and theory. A black hole at 2.6 solar masses would therefore raise a different problem. It would suggest either that stellar collapse can produce smaller black holes than expected, or that some other pathway exists. Perhaps through earlier mergers or unusual binary evolution. The object would still be real, but its origin would no longer be easy to place. This is why the signal becomes a boundary rather than only an event. It sits where 2 stories overlap without resolving into either one. On one side is the story of matter resisting gravity until it can resist no more. On the other is the story of gravity already victorious, leaving behind an event horizon and no surface to observe. Between them lies a narrow region where the instruments can weigh an object, but not immediately reveal what it is made of. A mass measurement alone is powerful, yet it is not always decisive. The same measured mass can belong to different kinds of compact objects if nature allows them. The problem becomes especially sharp because the merger did not produce a confirmed flash of light. When 2 neutron stars merged in an earlier gravitational wave event, telescopes saw light from the aftermath, including signals that revealed ejected material and heavy element formation. That light helped identify the nature of the objects involved. GW 190814 offered no such companion signal. No confirmed electromagnetic counterpart appeared to settle the matter. That silence may mean the smaller object was a black hole. It may also mean that a neutron star, if present, was swallowed by the larger black hole without being torn apart outside the horizon in a way that could make a visible flare. The absence of light, therefore, does not close the question. It only removes one path toward answering it. What remains is the gravitational evidence and the unease of a mass that refuses to sit comfortably in the old map. The larger object makes the system easier to understand in one sense and harder in another. A black hole of about 23 solar masses is not, by itself, surprising in the gravitational wave catalogue. Such objects had already become part of the new population revealed by LIGO and Virgo. Black holes larger than many found through older electromagnetic methods. But when paired with a much lighter companion, it changes the conditions of the final encounter. A neutron star approaching such a black hole might not be shredded early enough to leave debris outside. Whether it is torn apart depends on its size, the black hole mass, the black hole spin, and the exact geometry of the approach. If the black hole is too massive or the neutron star too compact, the smaller body crosses the point of no return before matter can escape. From outside, the merger becomes nearly dark. The distinction between a swallowed neutron star and a small black hole becomes faint, because both can leave gravitational waves without an obvious optical signature. The event therefore reveals the strength and the limit of the new astronomy at the same time. Gravitational waves can uncover hidden mergers across cosmic distances, including systems that light may never show. But when the classification depends on the internal nature of one compact body, even a clean signal can leave space for more than one interpretation. That space is not a failure. It is where the science begins to sharpen. Before gravitational wave detections, the boundary between neutron stars and black holes was inferred from separate populations, from pulsars, X-ray binaries, supernova models, and nuclear theory. Now the boundary is being tested directly by mergers involving objects that fall inside the uncertain region. Each such detection places pressure on old assumptions. It asks whether the mass gap is real or only a result of limited observations. It asks whether neutron stars can be heavier than expected, or whether black holes can form smaller than expected. It asks whether the categories themselves are too simple for the ways compact objects are made. GW 190814 does not answer all of these questions. Its importance is quieter and more durable. It marks a place on the map where the known populations almost touch, where one measured companion may be either the heaviest kind of star or the lightest kind of black hole. The signal has passed, the merger is long over, and no telescope has recovered the missing light. Yet the boundary it exposed remains active, not as a line drawn in theory, but as a physical frontier where matter, gravity, and observation meet without fully agreeing. The interferometer does not know that a star has died or that a black hole has grown. It only records distance, and even that distance changes by an amount so small that it seems almost incompatible with measurement. Inside LIGO and Virgo, laser light travels along long vacuum arms, reflects from suspended mirrors, and returns to be compared against itself. When no gravitational wave is passing, the returning beams maintain a steady relationship. When a wave crosses Earth, one arm is stretched while the other is compressed. Then the pattern reverses, and the light carries that change back as a shift in phase. The instrument is not catching matter or radiation in the usual sense. It is watching geometry move. That is why the evidence from GW 190814 begins in such an austere form. There is no image of the two bodies. There is no visible orbit traced against a background field. There is only a waveform, a narrow disturbance with a rising frequency and a growing strength, shaped by two compact masses losing orbital energy and drawing closer together. Yet within that line lies a remarkable amount of physical information, because general relativity does not treat the final spiral as random. It gives the motion a structure. As two compact objects orbit, they radiate gravitational waves. Those waves carry energy away from the system. The orbit tightens. The objects move faster. The wave frequency rises. The signal climbs in pitch and strength until the separate bodies can no longer be treated as separate in any simple way. This rising pattern is often called a chirp, not because it is gentle, but because the mathematics turns a catastrophic merger into a brief upward sweep. The exact way that sweep changes over time depends strongly on the masses involved. Heavy systems move through the detectors differently from lighter ones. Balanced pairs leave a different imprint than unequal pairs. Spins can alter the final motion, and distance affects the observed strength. In the case of GW 1908-14, the waveform carried the signature of a strongly unequal system. The heavier companion dominated the mass budget, while the smaller one contributed enough to shape the inspiral without making the pair symmetrical. That imbalance became part of the evidence. The signal was not merely detected, it was fitted against many possible models, each one representing a different combination of masses and spins consistent with Einstein's equations. This is where gravitational wave astronomy becomes both powerful and careful. The observatories do not simply listen and assign a mass by inspection. They compare the data with families of predicted waveforms, then ask which possibilities best match what passed through the detectors. Noise is always present. Earth moves. Mirrors tremble. Quantum fluctuations and thermal effects add their own limits. The signal has to be separated from that background without pretending that the instruments are perfect. For this reason, every measurement arrives with uncertainty. The smaller object is not known with infinite precision, but its mass falls squarely into the uncomfortable region near 2.5 solar masses. The uncertainty does not rescue it from the boundary. It places the boundary inside the measurement itself. The existence of multiple detectors matters because a gravitational wave reaches each site at a slightly different time. The LIGO detector in Louisiana, the LIGO detector in Washington, and Virgo in Italy form a scattered listening system across Earth. A wave passing through the planet touches them in sequence, and the tiny delays between detections help narrow the direction from which the signal came. The result is not a sharp celestial address, at least not for every event. Often it is a region on the sky, sometimes long and curved, containing many possible host galaxies. For GW 1908-14, this localization was good enough to guide follow-up searches, but not good enough to name a single galaxy with certainty. That matters because distance and environment would have added context. A known host could help describe the stellar population that made the system. A flash of light could reveal matter outside the black hole. A redshift could refine the cosmic setting. Without those additions, the gravitational wave carries most of the burden alone. It can still speak clearly about the compact objects, but it cannot fill every silence around them. The waveform also carries distance in a subtle way. A nearby merger produces a stronger signal than a distant one of the same intrinsic power, just as a nearby bell would sound louder than a far one if sound travelled cleanly through space. But gravitational wave distance is not measured by brightness in the ordinary optical sense. It is inferred from the amplitude of spacetime strain, adjusted through the model of the source. This creates a connection between what the system is and how far away it lies. Orientation complicates the matter. A merger seen face-on can appear stronger than one viewed edge-on. Spin and mass can influence the shape. The measurements therefore form a linked set rather than independent facts. The event is reconstructed through consistency. The masses must produce the observed frequency evolution. The distance must fit the signal strength. The arrival times must fit the sky position. The final parameters emerge from the overlap of all these constraints, not from any one clue in isolation. That layered method is why the small companion's mass cannot be dismissed as a simple observational accident. It is supported by the structure of the signal itself. The final spiral is especially revealing because compact objects in this regime move in a gravitational field so strong that Newtonian intuition becomes incomplete. Early in the orbit, Some of the motion can be approximated by familiar ideas of two bodies circling a common center. Near the end, the curvature becomes too intense for that picture to hold on its own. General relativity shapes the late-in spiral, the merger, and the ring-down, the fading vibration of the final black hole as it settles into a stable form. For black hole mergers, ring-down carries information about the mass and spin of the remnant. For systems involving neutron stars, the earlier motion may also contain tidal effects, small deformations caused by each body pulling on the other. Those effects depend on how easily a neutron star changes shape, which in turn depends on its internal structure. In GW 190814, however, the mass ratio and the likely swallowing of the smaller object limited what could be learned about tidal distortion. The signal weighed the object more clearly than it revealed its surface. This distinction is central. Gravitational waves can measure compactness through motion, but they do not always identify material composition. A black hole and a neutron star of the same mass can behave similarly in some parts of an in-spiral, especially if the neutron star is compact and is not torn apart before crossing the larger black hole's horizon. The absence of a strong tidal signature does not prove that the smaller object had no matter. It may only mean that any material effects were too small to separate from the dominant black hole dynamics. A surface can be hidden by circumstance. A star can vanish like a hole if it falls in cleanly enough. This is one of the quiet ironies of the event. The method that opened the system to observation also shows why classification remains difficult. Spacetime recorded the masses with enough clarity to reveal the problem, but not enough additional detail to solve it completely. What had once seemed like a clean division between object types became a narrow observational ambiguity. Still, the gravitational evidence changes the problem in a fundamental way. Before such detections, the dark side of compact object populations had to be inferred from systems that emitted light, such as pulsars and X-ray binaries. Those methods are powerful, but they favor objects that happen to beam radiation toward Earth, or feed on visible companions. Gravitational waves do not require a luminous environment. They can reveal compact objects that orbit in darkness, far from gas, far from any companion star that could make them shine. This means the new catalogue is not merely adding more examples to an old list. It is sampling a different population, one selected by merger rather than by light. GW 190814 may therefore be a sign that the apparent mass gap was partly shaped by how objects were previously found, or it may be a rare exception that confirms how unusual the gap region truly is. The evidence does not yet choose between those outcomes, but it makes both testable. Each future waveform becomes another measurement placed along the same uncertain boundary. For now, the signal stands as an example of what gravitational waves do best. They turn invisible motion into measurable structure. They allow a collision long finished and far beyond direct sight to become a set of physical constraints. They do not make the universe simpler. They make its hidden categories harder to ignore. In GW 190814, the detectors did not deliver a picture of the smaller body or a final name for it. They delivered something more exacting: a mass, an orbit, a merger, and a silence around all three. From those pieces, the boundary between neutron stars and black holes stops being a theoretical interval on a chart. It becomes an observed place, reached through a ripple that crossed Earth and left behind just enough evidence to weigh what could not yet be seen. The heavier body in GW 190814 removes one uncertainty early in the analysis. With a mass a little above 23 suns, it belongs to the black hole population revealed by gravitational wave astronomy, a population made of compact remnants too dark to see directly and too heavy to be mistaken for neutron stars. Its identity is not the part that unsettles the event. In the final orbit, it acts as the dominant gravitational well. the object around which the smaller companion is drawn into faster and faster motion. Yet its certainty creates the conditions for the deeper ambiguity. A black hole of that mass is massive enough to swallow a compact star, especially if the smaller body is dense. The event, therefore, gives the larger object a strange narrative role. It is the most massive member of the pair, but it is not the main mystery. It is the dark instrument that tests the smaller body by bringing it to the point where the difference between matter and horizon may no longer leave a visible trace. In older astronomy, a black hole often announces itself indirectly through what it does to surrounding material. Gas pulled from a companion star heats as it falls, glowing in X-rays before disappearing. Stars near a galactic center accelerate around an unseen mass. But an isolated stellar black hole, moving through space without gas nearby, is almost silent. Gravitational waves change that by allowing black holes to be found through their motion rather than their appetite. The larger object in this event belongs to that quieter class. Its existence is inferred from the way it shaped space-time during the inspiral. A body of more than 20 solar masses compressed inside its event horizon cannot be a neutron star under known physics. No known pressure of dense matter can support such a mass as a stable surface-bearing star. So the larger object anchors the system. It gives the event one fixed side of the boundary. Against that fixed side, the smaller object becomes harder to name. The difference in mass between the two companions matters. Equal mass black holes spiral together in a balanced dance, each pulling strongly on the other as the system loses energy. Here the smaller object was moving in the field of a much heavier one. The motion is still mutual, but the asymmetry is strong enough to make the lighter body feel almost like a probe sent into a deep relativistic environment. If it was a black hole, then the final act was a merger between two horizons of very different sizes. If it was a neutron star, then it approached a point where tidal forces may or may not have had time to tear it apart. Tidal forces are the difference in gravity between the near side and the far side of an object. Around a black hole, that difference can become severe. A neutron star passing close enough may be stretched and stripped, leaving hot debris outside the horizon. That debris can glow, form a disk, and sometimes help power a short burst of high-energy radiation. But the tearing has to happen before the star crosses the horizon. If disruption occurs too late, the material simply follows the star inward, and outside observers are left with gravitational waves alone. This is why the companion's nature is linked to the larger black hole's properties. The question is not only whether a 2.6 solar mass neutron star can exist, it is also whether, in this particular orbit, such a star could have left any sign of itself before vanishing. A larger neutron star, with a wider radius and less compact structure, would be easier to disrupt. A smaller and denser neutron star would behave more like a black hole in the waveform, because its surface would remain hidden until the last moments. The spin of the black hole also matters. If the hole spins in a way that allows the innermost stable orbit to sit closer to the horizon, a neutron star may travel deeper before being swallowed, changing the chance of debris remaining outside. If the spin is aligned and high enough, disruption becomes more plausible. If not, the encounter may be clean and dark. The gravitational wave measurement gives constraints on spin, but not enough to reconstruct every detail of the plunge with certainty. The absence of light, therefore, cannot be used as a simple verdict. It is a clue shaped by distance, geometry, detector limits, and the severe mass imbalance of the pair. The larger black hole makes silence expected even in some neutron star scenarios. It hides the evidence that might otherwise have answered the question. The event also presses on how compact object binaries are made. A 23 solar mass black hole paired with a much smaller companion is not just a final merger. It is the end of a long evolutionary history. Such a pair may have formed from two massive stars born together, each passing through stages of expansion, mass transfer, collapse, and orbital tightening. It may have formed dynamically in a dense stellar environment, where compact remnants sink toward the center of a cluster and exchange partners through close encounters. The large mass ratio does not choose one pathway by itself, but it makes the origin more interesting. In ordinary stellar evolution, creating a system where one remnant is a heavy black hole and the other lies exactly in the boundary region requires a delicate sequence. The first star must leave behind a substantial black hole. The second must produce either a very heavy neutron star or an unusually light black hole. The binary must survive supernova kicks, mass loss, and the complicated exchange of angular momentum. Then it must shrink enough for gravitational waves to bring the remnants together within the age of the universe. Each step can happen in principle, but the final pairing carries the imprint of all of them. In a dense cluster, the story changes. Compact objects can form separately, then become bound through gravitational interactions. A heavy black hole can replace a lighter object in an existing binary. Repeated encounters can assemble combinations that ordinary paired stellar evolution might rarely produce. A small black hole made by an earlier merger, or a massive neutron star formed through accretion, could later meet a heavier black hole and spiral inward. These channels remain uncertain because many environments can produce similar final waveforms. The gravitational wave tells the last seconds with exquisite discipline. It tells the earlier millions or billions of years only indirectly. That separation between the final measurement and the hidden origin is part of the event's pressure. The larger black hole is known, but its presence asks how such an unequal pair came to exist at all. Even the heavy object's familiarity has limits. Gravitational wave astronomy has shown that stellar mass black holes can be larger and more varied than the population first inferred from X-ray binaries. Some form in environments where massive stars lose less material before death, especially when they contain fewer heavy elements. Lower metallicity stars can retain more mass, leaving heavier cores and heavier black holes. This makes a 23 solar mass black hole plausible, though still informative. Its mass hints at the kind of star that may have formed it, and the history of winds and collapse that shaped its final remnant. But those clues remain broad. The heavier body is not exotic enough to break the map. Instead, it supplies a dark gravitational stage on which the smaller companion becomes almost impossible to ignore. A routine black hole, under the right circumstances, can expose a non-routine object beside it. The mass ratio also helps explain why the event is so cleanly troubling. If the smaller body had been closer to 10 solar masses, it would have joined the known black hole population without much concern. If it had been closer to 1.5 solar masses, it would have looked like a neutron star, even if the lack of light left some details open. At 2.6 solar masses, it occupies the region where both interpretations require effort. The larger black hole sharpens that placement by making the system credible as a black hole merger, while also allowing a neutron star to vanish without a trace. In that sense, the event is not ambiguous because the data are weak. It is ambiguous because nature has arranged the final encounter in a way that removes the easiest discriminating evidence. The dominant black hole gives gravity a clear signature and light almost nothing to work with. What remains is a companion weighed at the edge of two categories, carried into darkness by an object whose own identity is secure. The heavier body is therefore more than a background fact. It is the reason the smaller one can remain unresolved. It provides the horizon that may have swallowed matter before matter could announce itself. It provides the mass ratio that shaped the waveform and complicated the search for tidal traces. It provides one half of a binary history that must somehow produce an unlikely partner. Because it is clearly a black hole, the entire mystery is forced onto the companion. because it is massive. The companion may have been hidden, because it merged in darkness. The boundary between star and hole was not crossed in light, but in geometry. The smaller object carries the strange mass, but the larger one defines the silence around it. A neutron star is not held up by heat in the way an ordinary star is held up by fusion. By the time it exists as a neutron star, the luminous engine that once balanced gravity has already failed, and the core has passed through collapse into a stranger form of support. The object remains stable only because matter under extreme compression develops pressure from quantum rules and nuclear forces, a resistance that does not depend on burning fuel. This makes a neutron star feel almost like a final compromise between matter and gravity. It has not become a black hole, because some form of internal pressure still answers the inward pull, yet it is already so compact that the compromise cannot be widened very far. A little more mass does not simply make it a larger star. In the highest mass range, added weight can make the star more compressed, more relativistic, and closer to the point where the distinction between a surface and a horizon begins to close. This is why the smaller companion in GW 190814 creates such pressure on the theory. A neutron star near 2.6 solar masses would not be merely a heavy example of a familiar object. It would be a body surviving near the last possible margin before collapse becomes unavoidable. The limit begins with the collapse of a massive stellar core. In the life of an ordinary massive star, gravity is resisted for millions of years by the energy released in fusion. As lighter elements merge into heavier ones and provide outward pressure, that support ends in stages. Once the core becomes dominated by iron, fusion can no longer release energy in the same sustaining way. The balance fails, and gravity acts quickly. The core contracts, electrons and protons are forced together, neutrinos escape in enormous numbers. The outer layers may be driven outward in a supernova, while the central remnant becomes one of the densest long-lived objects in the universe. The word neutron star gives the impression of simplicity, as though the object were only a sphere of neutrons. The real structure is more layered and more uncertain. Near the surface, nuclei may remain in a crust. Deeper down, nuclei become distorted, packed into unusual shapes by pressure. Below that, matter approaches and exceeds the density found inside atomic nuclei. The core becomes an arena where ordinary descriptions grow less secure. What matters for stability is how all of those layers respond when gravity demands more compression. In an ordinary planet or main sequence star, adding mass often increases size, at least over broad ranges, because more material occupies more space and pressure gradients adjust. A neutron star does not obey that simple expectation. Its matter is already squeezed so tightly that gravity, quantum degeneracy, and nuclear interactions are locked in a delicate contest. Degeneracy pressure arises because certain particles cannot all occupy the same quantum state. When matter is compressed, that rule produces resistance. For white dwarfs, electron degeneracy pressure can hold up a stellar remnant until a known mass threshold is reached. For neutron stars, neutron degeneracy pressure and the strong nuclear force join the problem, but general relativity makes the contest harsher. Gravity is not merely a force acting through space. In Einstein's theory, mass and energy curve spacetime, and pressure itself also contributes to the gravitational field. Inside a neutron star, the pressure needed to resist collapse becomes part of what gravity must act upon. Stability, therefore, becomes less intuitive. More pressure helps hold the object up, but in relativistic conditions, it also adds to the source of gravity. The star is fighting with tools that become heavier as they are used. The maximum mass of a neutron star is sometimes described as the point where no stable solution remains. Below that point, a possible arrangement exists in which pressure increases inward. Gravity pulls inward, and the star maintains a surface. Above it, the equations no longer permit a static object of that kind. No known signal can cross outward fast enough to restore balance. Collapse proceeds toward a black hole. This theoretical maximum is not a single number known from pure reasoning alone, because it depends on the equation of state of dense matter. The equation of state tells how pressure changes with density and temperature. In the cold, mature interior of a neutron star. Temperature is less important than compression and composition. A stiff equation of state means pressure rises strongly as density increases, allowing the star to support more mass. A soft equation of state gives less resistance, leading to collapse at lower mass. The difficulty is that the relevant densities exceed what terrestrial experiments can reproduce in bulk. Particle accelerators can create extreme conditions for tiny moments, and nuclear theory can guide the calculation. But the core of a neutron star remains a natural laboratory beyond direct reach. The deeper the star is examined in theory, the less certain the composition becomes. At moderate depths, neutrons may dominate. At greater densities, the neutrons may overlap so strongly that their internal structure matters. Neutrons are made of quarks, and under sufficient pressure, quarks may no longer stay confined in the ordinary way. Some models allow matter containing strange quarks, forming phases different from the nuclear material near the outer core. Others propose hyperons, particles heavier than neutrons, appearing in the interior. These possibilities are not decorative details. They change the equation of state. New particle species can give matter additional ways to arrange itself, often softening the pressure and lowering the maximum mass. But observations of very massive pulsars already restrict how soft the interior can be. Any model that collapses too early cannot explain neutron stars measured above 2 solar masses. This creates a narrowing corridor. The interior must be exotic enough to follow nuclear physics under extreme density, but not so soft that known heavy neutron stars become impossible. GW 190814 presses at the far end of that corridor. The idea of a surface is central to the boundary. A neutron star has one, even if it is not a surface in any gentle sense. There is a place where matter ends and space begins, a region from which light can still escape if it is emitted in the right direction with enough energy. A black hole has no such surface visible to the outside. It has an event horizon, a boundary in space-time beyond which all future paths lead inward. For any mass, there is a corresponding size at which a horizon would form if the mass were compressed inside it. For Earth, that size is tiny compared with the planet itself. For the Sun, it is only a few kilometers across. For a neutron star, the horizon scale is already close to the star's physical size. The star's real surface and its possible horizon are neighbours in a way almost no ordinary object can approach. As mass increases, the gravitational radius grows. If the star's radius shrinks or fails to grow enough, the two boundaries move toward each other. At the maximum mass, the question is no longer whether the star is dense. It is whether any surface can remain outside the radius from which light cannot return. Rotation can complicate this picture. A rapidly spinning neutron star can support slightly more mass than a non-spinning one, because rotation provides additional support against collapse. This is not a permanent escape. As the star loses rotational energy over time, or if it gains mass through accretion, the extra margin can disappear. Magnetic fields, temperature, and the history of formation can also influence details, but the cold, non-rotating maximum remains a central reference point. A neutron star born in a merger may briefly exceed the ordinary limit if it is hot, differentially rotating, or supported by violent internal motion. Such objects can survive for milliseconds, seconds, or longer before collapsing. but the smaller companion in GW 190814, if it was a neutron star, had to exist before the merger as a compact object in orbit around a black hole. It could not rely on the temporary support of a newly formed remnant. Its mass would therefore speak to the stable, or nearly stable limit of neutron star matter, not merely to a transient aftermath. This is why the distinction is so demanding. A confirmed neutron star at about 2.6 solar masses would force the maximum mass upward, or at least force models to allow stability close to that value. Many softer interior models would become difficult to preserve. Dense matter would need to remain more resistant under compression than those models predict. The star would become an argument for stiffness, for pressure that can keep acting even when the center may contain forms of matter far beyond ordinary nuclei. But if the maximum mass lies lower, as several lines of evidence suggest, then the object cannot have been a stable neutron star. It must have crossed the boundary already. The same measured mass would then belong not to matter under final pressure, but to a black hole formed by some less common root. The limit is therefore not an abstract number in a table. It decides whether the companion had a surface, whether its interior held nuclear matter, whether its final approach involved material deformation, and whether its silence was the silence of swallowing or the silence of a horizon from the beginning. In this way, neutron star physics turns the event into a test of matter itself. The smaller body did not need to shine to become important. Its mass alone placed it against the question of how much weight nature can pack into a star before the word star no longer applies. Somewhere between the heavier supported core and the lightest horizon, the pressure inside matter stops being enough. GW 190814 arrived from that region, carrying no direct image of a surface and no final confession from the object that crossed the larger black hole's edge. It left behind the shape of an orbit and the weight of a companion, and those are enough to make the neutron star limit feel less like a theoretical ceiling than a threshold being touched in the dark. Deep inside a neutron star, the familiar language of matter begins to lose its ordinary meanings. At the surface, there may still be atoms stripped and compressed into a thin atmosphere, and beneath that, nuclei locked into a crust of extraordinary strength. Farther down, the spacing between particles becomes so small that the distinction between one nucleus and the next starts to fail. Matter is no longer arranged in the loose architecture of ordinary solids, liquids, or gases. It becomes a crowded quantum system, dominated by particles packed close to the density of an atomic nucleus, and then driven beyond it. The central question is not simply what is inside the star, but how that interior pushes back when gravity demands more compression. That response decides whether a neutron star can remain a star. It decides whether 2.6 solar masses can still have a surface, or whether such a mass must already have crossed into the black hole side of the boundary. The difficulty is that the core is hidden by design. No telescope can look through the crust and inspect the layers directly. Light escaping from the surface has already been shaped by gravity, magnetic fields, and the thin outer regions. Gravitational waves may reveal deformation during a merger, but only under favourable conditions. Pulsar timing can weigh a neutron star with great precision, but mass alone does not reveal composition. Every method touches the interior indirectly. The result is a strange form of knowledge, precise at the edges and uncertain in the centre. Radius, cooling, spin, tidal deformation, and maximum mass all become clues to the same buried physics. None is the core itself. Each is an imprint left by matter that cannot be brought into a laboratory in the same form. Near the outer crust, the pressure is already far beyond ordinary experience, but the ingredients remain somewhat recognizable. Nuclei form a lattice, immersed in a sea of electrons. Deeper in, Neutrons begin to leak out of nuclei, no longer bound to individual atomic structures. The crust becomes a mixture of nuclei, free neutrons and electrons. Near the base of the crust, theory predicts that nuclei may deform into elongated rods, flat sheets, and other shapes sometimes called nuclear pasta. These shapes form because nuclear attraction and electric repulsion compete under extreme compression. They may affect how the crust breaks, how heat moves, and how the star responds to stress. Even this outer region, better understood than the core, shows that neutron star matter does not move cleanly from one familiar state to another. It passes through forms that exist because gravity has forced nuclear physics into unusual arrangements. The core brings a harder uncertainty. At densities around and above nuclear density, matter may consist mostly of neutrons with a smaller number of protons, electrons, and other particles needed for balance. The pressure depends on how strongly neutrons repel each other at short distances, and on how energy changes when the proportions of neutrons and protons shift. One important part of this is called the symmetry energy, which describes the cost of making matter more neutron-rich. It affects the radius of the star and the stiffness of the interior. A stronger pressure at these densities tends to produce larger radii and greater resistance to collapse. A weaker pressure allows the star to compress more. But theory cannot simply choose any behavior it wants. It must match nuclear experiments, observed pulsar masses, gravitational wave data, and the basic rules of causality, which forbid pressure signals from travelling faster than light. The core must be stiff enough to support known heavy neutron stars, yet not so stiff that it conflicts with measured deformability and radius estimates. This tension makes the interior a constrained mystery rather than an open fantasy. At still greater depth, the particles themselves may change. Neutrons and protons are not fundamental points. They are made of quarks held together by the strong force. In ordinary nuclei, those quarks remain confined inside their parent particles. But when pressure becomes immense, confinement may weaken or reorganize. Some models allow quark matter to appear in the inner core, where up, down, and perhaps strange quarks move through a more continuous state. Other models introduce hyperons, heavier relatives of neutrons and protons that contain strange quarks inside them. These new ingredients are tempting because they follow naturally from particle physics under enough energy and density. Yet they create a problem. When new particle types appear, they often give matter more ways to share energy, which can reduce pressure. That softening makes it harder to support very massive neutron stars. This is sometimes called the hyperon puzzle. Physics seems to allow new particles, but observations demand that the star remain strong. Any proposed interior must solve both sides at once. It must allow the microphysics to be plausible and still keep gravity from winning too soon. Phase transitions make the problem even sharper. A phase transition is a change in the state of matter, like water becoming ice. Though inside a neutron star, the change may involve nuclear matter turning into quark matter, or another exotic phase. If such a transition is gentle, the star's structure may shift gradually as density increases. If it is abrupt, the inner core could change suddenly once a threshold is crossed. Some models allow two stars with similar masses but different radii because one contains a transformed core while the other does not. In that picture, the boundary between ordinary neutron-rich matter and more exotic matter could leave an imprint on the mass-radius relation, the curve that tells which sizes are possible for which masses. A heavy object near 2.6 solar masses would place severe pressure on such models. If it were a neutron star, its central pressure would likely reach the region where many transitions become unavoidable. The question would no longer be whether exotic matter might appear, but whether it can appear without making the star collapse. The merger of two neutron stars observed in an earlier gravitational wave event added another kind of clue. As neutron stars orbit each other, Each one is distorted by the tidal field of the other. The amount of distortion depends on compactness and internal stiffness. A puffier star deforms more. A more compact star resists the tide more strongly. The measured tidal deformability from such events can limit possible radii and equations of state. The light that followed that merger also mattered, because the amount and behaviour of ejected matter helped infer what kind of remnant formed and how long it survived before becoming a black hole. These clues suggested that neutron stars cannot be arbitrarily large or arbitrarily stiff. They must fit both the gravitational wave signal and the electromagnetic aftermath. Yet the same universe also contains pulsars above two solar masses, showing that the interior cannot be too soft. Dense matter is therefore caught between lower and upper pressures, between collapse on one side and excessive size on the other. The companion in GW 190814 lies near the upper edge of that struggle. If it had a surface, the core beneath that surface would be among the most compressed stable interiors ever inferred. A neutron star at that mass would require an equation of state able to bear enormous central density without giving way to a phase that softens too much. It might imply that repulsive nuclear forces remain powerful deep into the core, or that quark matter, if present, behaves in a surprisingly stiff way. It might narrow the range of allowed phase transitions, ruling out those that trigger collapse before such a mass is reached. It would also affect the interpretation of other mergers, because the threshold for prompt collapse after neutron star collisions depends on the maximum mass of non-rotating stars. A higher maximum would let merger remnants survive longer. A lower maximum would make collapse more immediate. One object near the boundary would therefore reach beyond itself, altering how many other compact events are read. If the companion was not a neutron star, dense matter still remains at the centre of the argument by exclusion. A low maximum mass would help identify the object as a black hole, because it would make stable matter at 2.6 solar masses impossible. In that case, the absence of a surface would not be directly seen but inferred through the failure of matter to support such weight. The black hole interpretation would still depend on neutron star physics, because the border has to be drawn before an object can be placed beyond it. This is what makes the boundary unusually delicate. It is not defined by a visible wall. It is defined by the last successful arrangement of pressure against gravity. The core's hidden composition decides where that arrangement ends. The mystery of GW 190814 is therefore not only a question of classification, it is a question about the strong force in one of the few places where nature has built a macroscopic object out of nuclear density matter. Whether the smaller companion was the heaviest kind of neutron star or the lightest kind of black hole, its mass passes through the same narrow gate of interpretation. On one side, matter finds a way to remain matter. On the other, no internal structure remains visible to the outside universe. The difference may depend on particles and pressures buried kilometers beneath a surface that no light from the merger ever revealed. Between the heaviest confirmed neutron stars and the lightest familiar black holes, astronomy has long seemed to find a pause. In theory, equations can be written for objects close to the boundary, and simulations can follow collapsing stars into many outcomes. Yet in observation, the interval has been strangely quiet. Neutron stars measured through pulsars tend to cluster near 1.5 solar masses, with a few reaching beyond 2. Black holes found through X-ray binaries have usually appeared at several solar masses and above. Between them lies the so-called mass gap, a zone where compact objects should be difficult to classify and, until recently, difficult to find. The smaller companion in GW 190814 lands almost exactly where that quiet has mattered most. It asks whether the gap is a real feature of stellar death, an illusion created by the way objects were discovered, or a frontier that nature crosses only through rare channels. The reason a gap might exist begins with how massive stars end. A star is not free to choose any remnant mass smoothly. Its final state depends on the mass of its core, the layers around it, its rotation, its composition, and whether it lives alone or exchanges material with a companion. When the core can collapse and then rebound into a successful supernova, much of the outer material is driven away, leaving a neutron star behind. When collapse is too strong, the rebound may fail, or fall back may add material to the compact remnant, helping form a black hole. The transition between those outcomes is not expected to be gentle. Once an event horizon forms, infalling matter that might have been expelled can instead be swallowed. That can push the remnant mass upward, leaving fewer black holes just above the neutron star limit. The gap, in this view, is a scar left by the violence of collapse. It marks not a law of gravity, but a discontinuity in the engines that make compact objects. Observations before gravitational wave astronomy reinforced this picture, though never without uncertainty. Neutron star masses could be measured most cleanly in binary pulsar systems, where the timing of radio pulses reveals orbital motion with extraordinary precision. Those systems showed a narrow but not identical family of masses. The discovery of pulsars above two solar masses placed a firm lower bound on the maximum mass that dense matter must support: black holes. Meanwhile, were often weighed in systems where they pulled gas from a visible star. The companion star moved under the gravity of an unseen object, and the glowing accretion flow marked the system as active. These black holes usually appeared heavier than about 5 solar masses. The absence of objects between the two groups looked meaningful, but it came from methods that favoured particular kinds of systems. Pulsars had to beam toward Earth. X-ray binaries had to feed. Quiet, compact objects in the gap could have existed without offering either signal. This selection problem matters because astronomy often mistakes the easiest objects to see for the most common objects that exist. A neutron star with an unfavourable beam may be invisible as a pulsar. A black hole without nearby gas may not shine. A compact object in a wide binary may reveal itself only weakly through a companion's motion, and an isolated one may drift through the galaxy with almost no trace. The mass gap could therefore be partly observational, produced by the narrow doors through which compact objects enter the catalogue. Gravitational waves widen those doors, but in a different direction. They find objects not because they shine, but because they merge. This means the gravitational wave population is shaped by its own selection effects. It favours compact binaries that have tightened enough to collide. Systems whose histories may differ from the compact objects found through radio or X-ray light. Still, it can reach into dark populations that older methods missed. GW 190814 is powerful for that reason. It finds a boundary object through motion alone, in a place where light had provided too few examples. If the mass gap is astrophysical, the object becomes rare by nature. If the gap is observational, it becomes one of the first clear signs that the silence was never complete. But either interpretation has consequences. A genuine gap would mean that the formation channels for compact remnants avoid certain masses most of the time. Stellar cores would either stabilize as neutron stars below a threshold, or collapse into black holes with enough additional material to leap over the intermediate range. It would also constrain how often neutron stars can grow through accretion or mergers without collapsing. A filled gap, by contrast, would mean that nature produces boundary objects more readily than the older catalogue suggested. Low-mass black holes might form through weak explosions, stripped stars in binaries, or the collapse of massive neutron stars after gaining matter. Very heavy neutron stars might survive if dense matter is stiff enough. The same region could even contain both object types, overlapping in mass while differing in structure. In that case, mass alone would cease to be a reliable name tag. The boundary would have to be read through additional clues, such as tidal deformation, electromagnetic emission, spin, and formation environment. The lower edge of the black hole population is especially sensitive to stellar physics. Real stars do not obey a tidy sequence in which one initial mass always gives a neutron star, and a slightly larger one always gives a black hole. Winds remove mass, cores rotate or mix, and binary companions can strip envelopes away or transfer material before the final collapse. The explosion itself is governed by neutrinos, turbulence, and the struggle to revive a stalled shock wave after the core rebounds. Small differences in these processes can change whether the outcome is a neutron star, a black hole formed after fallback, or a failed explosion that collapses more directly. A low-mass black hole near the gap would be evidence that some pathway can form a horizon without adding several solar masses of material. That would not be impossible, but it would remove the comfort of a clean minimum. The upper edge of the neutron star population is equally demanding. The most massive pulsars already show that neutron stars can grow well beyond the canonical mass often associated with their birth. Some of that growth may come from accretion in binary systems, especially in millisecond pulsars spun up by material from a companion. But accretion has limits. Transferred matter carries angular momentum, heats the surface, and may trigger instabilities. A neutron star approaching the maximum mass is never simply becoming heavier in an ordinary way. It is moving closer to collapse with each added layer. If stable neutron stars can reach the mass of the GW 190814 companion, then the mass gap would shrink from below. The heavier stars would press upward into territory once reserved for black holes. If they cannot, then the object must be explained through black hole formation instead. The gap becomes a meeting place between nuclear matter and stellar death, not merely a range on a graph. The silence of the gap may also hide multiple populations rather than one missing class. Some objects could be neutron stars formed massive at birth. Others could be neutron stars enlarged by long accretion. Some could be black holes made by unusual supernova fallback. Others could be second-generation black holes, formed when earlier compact objects merged and later joined a new binary, in dense clusters. Repeated encounters can exchange partners and build systems that would be rare in isolated stellar evolution. A black hole in the gap might therefore be old in a different sense, not the direct corpse of one star, but the remnant of a previous collision. Its mass would carry a history of assembly. A neutron star in the same range would carry a history of survival. Both could occupy the same interval while pointing to different cosmic environments. This possibility turns the mass gap from a simple absence into a layered diagnostic, a way of asking which histories are common enough to leave detectable mergers. GW 190814 does not fill the gap by itself. One object cannot define a population, especially when its identity remains uncertain. But it weakens the idea that the gap can be treated as comfortably empty. It shows that the interval is observationally reachable and physically inhabited by at least one compact body, even if the nature of that body remains unresolved. A gap that has never been sampled can be imagined as a clean division. A gap containing an object becomes a problem of classification, formation, and statistics. Future detections may reveal a smooth distribution, a few isolated exceptions, or a structured landscape with different channels leaving objects at different masses. Each outcome would point to a different story of how stars collapse, how binaries evolve, and how dense matter fails or survives. The missing population, if it exists, may not announce itself as missing for much longer. It may arrive as more waveforms, each one weighing a compact body that light has not named. The old map placed neutron stars on one side and black holes on the other, with a quiet interval between them. GW 190814 placed weight inside that interval. Whether the companion was a final star or small horizon, it changed the gap from an absence into a question with mass. The silence around GW 190814 is not empty. It is one of the facts that has to be interpreted. After the gravitational wave passed through the detectors, telescopes searched the region of sky from which the signal most likely came, looking for any brief flare that might reveal matter torn from the smaller object. They found no confirmed counterpart, no optical glow, no clear burst across other wavelengths, no expanding ember that could be tied securely to the merger. In an ordinary sense, nothing was seen. But in this case, absence does not behave like a simple answer. A dark merger can mean that both bodies were black holes, each already defined by horizons and unable to produce light on their own. It can also mean that a neutron star was present, but entered the larger black hole too cleanly to leave debris outside. The same silence can belong to two different endings. One is the silence of an object that never had a surface. The other is the silence of a surface erased before it could speak. The search for light was shaped by an earlier success. When the binary neutron star merger GW 170817 was detected, it did not remain only a gravitational wave event. Telescopes found a fading source in a nearby galaxy, and that light carried a second story. Material had been thrown outward. Heavy elements were forged in neutron-rich debris. The glow evolved over days as radioactive decay heated the expanding matter. That event became a landmark because gravity and light described the same collision from different sides. The waveform revealed the masses and orbit. The light revealed matter in motion after the merger. Together they showed that some compact collisions can be read as both geometry and fire. GW 190814 offered no such double view. Its gravitational signal was clear, but the sky did not provide the same added layer. The comparison is tempting, but it has to be handled carefully, because the two events were not the same kind of encounter. In a merger of two neutron stars, both objects have matter outside any horizon. As they approach, tidal forces can tear material away, and the collision itself can eject hot neutron-rich matter into space. If the remnant survives even briefly before collapse, winds from a disk or from the remnant can add more material to the outflow. Those conditions make light plausible. A black hole and neutron star merger is more conditional. The neutron star must be disrupted outside the black hole's event horizon. If it is torn apart early enough, matter can form a disk, power radiation, and perhaps generate a kilonova-like glow. If not, the star crosses the horizon almost intact, and little or no material remains to shine. The result depends on a balance of sizes and distances, the radius of the neutron star, the mass of the black hole's spin, and the orbit's orientation. The physics is not merely whether matter exists, it is whether matter is given time and space to escape. The larger black hole in GW 190814 makes that escape difficult. With a mass above 20 solar masses, it has a horizon and an innermost stable orbit on scales that can swallow the smaller object before tidal disruption becomes visible. A lower mass black hole would give a neutron star more opportunity to be torn apart outside the horizon. A rapidly spinning black hole, if its spin were aligned with the orbit, could also alter the geometry in a way that makes disruption more likely. But a massive black hole with unfavourable spin can behave like a nearly perfect absorber. The neutron star may stretch in the final moments, but if that stretching happens inside the region from which no signal can return, the outside universe receives almost nothing from the material nature of the object. In that circumstance, the lack of light would not argue strongly against a neutron star. It would only show that the black hole allowed little debris to remain outside. The distance to the event adds another layer of caution. A counterpart like the one seen after GW 170817 would become much harder to detect if it occurred far enough away, especially if the ejector were faint, the viewing angle unfavourable, or the sky localization broad. Telescopes can search large areas quickly, but they cannot make a dim signal bright, and they cannot remove every source of confusion from crowded fields of galaxies. A kilonova fades, it changes colour. It must be found before it slips below detection limits. If the merger occurred in a distant or poorly placed host, even a real electromagnetic signal could have escaped identification. The absence of a confirmed counterpart therefore includes the limits of the search itself. It says no light was found with confidence. It does not prove that no photons were ever produced. It narrows the possibilities, but not to a single line. This is the discipline required when darkness becomes evidence. It is easy to treat no detection as a negative fact, and sometimes that is justified. If an event is nearby, well localized, and expected to produce a bright signal, then silence becomes restrictive. But GW 190814 sits in a less forgiving category. The system was asymmetric. The black hole was massive. The smaller body, if it was a neutron star, may have been exceptionally compact. The event was not close enough for every faint glow to be safely ruled out. These conditions turn non-detection into a softer constraint. It can weigh against scenarios that require abundant ejector, but it cannot eliminate scenarios in which little matter escapes. A neutron star with a small radius, swallowed promptly by a heavy black hole, could leave almost the same observational aftermath as a low-mass black hole. The surface would exist until the plunge, but the universe outside would not receive an obvious announcement of it. The possibility of a small black hole remains simpler in one respect. If the companion was already a black hole, then the lack of light is exactly what would be expected from a clean black hole merger in an environment without gas. Two horizons merge, gravitational waves carry away energy, and the final black hole settles through ringdown. No surface is torn. No nuclear matter is decompressed. No heavy element-rich debris spreads into space. The event would belong to the dark population that gravitational wave detectors were built to find. The problem is not the darkness. The problem is the mass. A black hole at about 2.6 solar masses would be unusually light by the standards of the older stellar black hole population. The silence fits that interpretation, but the weight resists it. A neutron star interpretation reverses the tension. The weight is difficult but possibly informative, while the silence becomes a matter of swallowing geometry. Neither path is free of complication. The missing light also matters because electromagnetic emission can reveal properties that gravitational waves alone may leave uncertain. A kilonova would have pointed toward neutron-rich matter outside the horizon. Its brightness and colour could have helped estimate the amount of ejected mass, which in turn would have offered clues about the neutron star radius and the black hole spin. A short gamma-ray burst, if detected and associated, could have suggested a relativistic jet, though such jets depend strongly on viewing angle and environment. X-rays or radio emission might have traced afterglow from material interacting with surrounding gas. Any of these signals would have added another constraint. Without them, the event remains weighted toward geometry rather than chemistry. The gravitational wave tells that a compact object merged. It does not show a process material, disk winds, or a fading thermal glow. The object is weighed, but its material remains unhandled. There is a quieter symmetry in that result. Neutron stars are valuable partly because they expose matter under extreme pressure, and when they are torn apart, they release pieces of that matter into space. Black holes are valuable because they expose gravity under extreme curvature, but they hide whatever crosses the horizon. A black hole neutron-star merger sits between these two forms of knowledge. If disruption occurs, the neutron star turns briefly into a laboratory without walls, scattering its interior into observable debris. If disruption fails, the black hole enforces privacy. It takes the star whole enough that the information about its surface and composition is carried inward. GW 190814 appears to fall near the second outcome, whether or not a neutron star was present at all. Its silence is therefore not only an observational inconvenience, it is part of the physical character of the event a boundary object encountered under conditions that may have hidden the very signs needed to name it. That does not make the search for counterparts unimportant. It makes every future counterpart more valuable. One confirmed flash from a similar mass system could transform the interpretation of the boundary. It could prove that at least some objects in this range have matter outside a horizon. It could show that neutron stars near the maximum mass can be disrupted, or that black hole spin can rescue debris even in unequal mergers. Conversely, a growing set of dark events in the same mass range would not prove that all such objects are black holes, but it would strengthen the case for either small horizons or very compact neutron stars swallowed without display. The pattern will matter more than any single non-detection. Light is a verdict only when it appears. Darkness is slower. It becomes meaningful through repetition, through context, and through the narrowing of what could have been missed. For GW 190814, the sky remained dark, and that darkness left the smaller object suspended between two interpretations. If it was a black hole, the silence was natural but the mass was strange. If it was a neutron star, the mass was extreme and the silence was possible, because the larger black hole may have erased the evidence before it could escape. The event did not fail to speak. It spoke in only one language, the language of space-time strain, while the language of light stayed unavailable. That is why the merger remains so carefully unresolved. It shows how a compact object can be measured with remarkable precision and still keep its surface, if it had one, beyond reach. If the smaller companion in GW 190814 was a neutron star, then it was not simply a neutron star with an unusually large number attached to it. It was a direct challenge to the last stable arrangements of dense matter. A star of about 2.6 solar masses would sit near the upper boundary of what nuclear physics can plausibly support, pressing against the range where many equations of state begin to fail. The issue is not that such a mass is unimaginable in the abstract. The issue is that a neutron star at that mass must keep a surface outside its own gravitational radius, while its core bears a weight so intense that many possible forms of matter would soften, rearrange, or collapse. It would have to remain compact enough to fit the gravitational wave evidence, yet stiff enough internally to avoid becoming a black hole before the merger ever began. That combination would make it one of nature's most severe tests of matter under pressure. A confirmed neutron star in this range would immediately sharpen the maximum mass problem. The maximum is not just a record to be broken. It is a physical boundary set by the balance between gravity and the pressure created by dense matter. Every measured heavy pulsar already pushes that boundary upward, ruling out models that collapse too early. A 2.6 solar mass neutron star would push it much farther. Equations of state that allow strong softening at high density would become difficult to keep, unless some additional stiffening appears at still greater compression. Models with hyperons, quark phases, or other exotic components would not be excluded simply because they are exotic, but they would have to survive a harsher test. They could not reduce pressure so much that the star loses stability below the observed mass. In that sense, the object would not merely tell astronomers that neutron stars can be heavy. It would tell nuclear physicists that matter, even when transformed in the core, must keep resisting collapse strongly. This would also affect the way radii are understood. A heavy neutron star is not allowed to be large without limit, because gravitational wave observations from other mergers constrain how easily neutron stars deform under tidal forces. A very stiff equation of state can support high mass, but it often produces larger radii and greater tidal deformability. A very soft one may match smaller radii but fail to support heavy stars. The allowed solution may lie in a more subtle interior, one that is moderately soft at certain densities and stiffens at others, or one in which phase transitions occur without destroying the star's ability to bear weight. Such behavior would make the mass-radius relation more complex than a simple smooth curve. It might allow ordinary mass neutron stars to remain fairly compact, while still permitting the most massive ones to survive. The survival of such an object would also speak to formation. Neutron stars are often born with masses lower than this, closer to the familiar range around 1.5 solar masses. To reach the boundary, a star may need to be born unusually heavy, or gain mass over time from a companion. Accretion can add material gradually, spinning the star up and changing its thermal and magnetic history. But it cannot go on without consequence. Each added layer brings the star closer to collapse. If the companion in GW 190814 was a neutron star, then its past must include a path that built or preserved such an extreme mass without crossing the limit. In a binary with a massive black hole, that path becomes even more demanding. The system must form, survive the violent births of both compact remnants, and remain bound long enough for gravitational waves to draw the orbit inward. The neutron star would carry not only the physics of its interior, but a difficult history of assembly. It would be a survivor in two senses, supported against gravity within itself, and preserved through the disruptive evolution that brought it to the black hole. Rotation offers one possible margin, but it does not dissolve the problem. A spinning neutron star can support more mass than a non-spinning one, because the outward effect of rotation reduces the burden on pressure. Yet the gravitational wave signal did not provide a simple way to claim that the object was saved by extreme spin. Very rapid rotation would have its own consequences, including deformation, possible instability, and a formation history that must explain how such spin was maintained until merger. Uniform rotation can extend stability, but only by a limited amount. Differential rotation, where different layers spin at different rates, can support much larger temporary masses in fresh merger remnants. But that is not the condition expected for an old compact object in a binary. A long-lived neutron star approaching a black hole would likely have had time to settle away from the most violent temporary states. If rotation helped, it could have widened the margin, but it would not turn the object into an ordinary neutron star. It would still remain close to the edge. The tidal behavior of such a star would be especially important, though difficult to observe in this event. A less compact neutron star would be more easily stretched and perhaps torn apart before crossing the black hole's horizon. A more compact one would resist deformation and be swallowed more cleanly. For a 2.6 solar mass neutron star, many plausible models predict a relatively small radius, because high mass tends to compress the star. That compactness would make tidal effects harder to detect and electromagnetic debris less likely. This creates a quiet consistency within the neutron star interpretation. The same properties needed for the star to survive at high mass may also help explain why it left no visible flash. It could have been dense, tightly bound, and difficult to disrupt, crossing into the larger black hole with little matter escaping. The interpretation remains demanding, but not incoherent. A heavy neutron star could hide itself by being almost too compact to reveal the fact that it was matter. If confirmed, the implications would extend to neutron star mergers beyond this single event. The maximum mass controls what happens when two neutron stars collide. If their combined remnant exceeds the stable limit by too much, collapse into a black hole may occur almost immediately. If the limit is higher, the remnant may survive for longer, supported briefly by heat, rotation, and internal motion. That survival time influences how much matter is ejected, how bright a kilonova becomes, whether a disk forms, and how energy is released into the surroundings. A higher stable maximum would shift the interpretation of previous and future mergers. It would affect the threshold for prompt collapse and the expected range of electromagnetic counterparts. The companion in GW 190814 would therefore become a calibration point for many other events, a single heavy object altering the meaning of a wider catalogue. The neutron star possibility also softens the apparent mass gap from above. If matter can support a star at this mass, then the gap between neutron stars and black holes is narrower than it once seemed. The upper edge of neutron stars would move closer to the lower edge of black holes, and the clean separation between the two populations would weaken. That does not mean all boundary objects would be neutron stars. It means the same mass range could contain different kinds of compact bodies, depending on formation path, spin, and internal composition. The word neutron star would no longer imply a familiar mass scale. It would include objects so close to collapse that their surfaces are almost hidden by their compactness. The category would stretch toward the horizon, not as speculation alone, but as a consequence of measured survival. The question would no longer be simply how heavy the object is, but whether it deforms, whether it shines when disrupted, how it formed, and how its mass fits the broader population. Still, caution remains essential. A mass near 2.6 solar masses is a difficult place to place a neutron star, and without a direct sign of matter, the interpretation cannot be secured. The gravitational wave did not show an unmistakable tidal imprint. The sky did not reveal ejected material. No pulsar timing measurement weighs this object in a quiet binary, where its identity could be established by emission. The neutron star case is therefore a conditional doorway. If it was matter, then dense matter is stronger, stranger, or more carefully structured than many models allow. If it was not, then the maximum mass likely lies below it, and the event belongs to the black hole side. The power of the neutron star possibility is that it describes what would have to be true for the object to survive. It outlines the physics demanded by a surface at the edge. In that version of the event, the smaller companion becomes a final star, carrying the weight of more than 2 suns into the gravitational field of a black hole and remaining matter until the last moment. Its surface would not have announced itself in light, but its existence would still echo through dense matter theory. The star would have crossed the boundary only at the end, not before. And in that brief distinction lies the entire importance of the possibility gravity may have won during the merger, but until then, matter may have held. If the smaller companion in GW 190814 was a black hole, then the event becomes strange in a different direction. The problem moves away from the maximum strength of dense matter and toward the minimum mass of a horizon made by stellar evolution. A black hole of about 2.6 solar masses is not forbidden by general relativity. Once enough mass is compressed inside its own gravitational radius, an event horizon forms, no matter whether the mass is enormous or modest by cosmic standards. The equations themselves do not object to a small stellar black hole. What makes the interpretation difficult is the route by which nature would have made it. Ordinary massive stars do not seem to leave black holes at every possible mass. Their deaths involve explosions, fallback, mass loss, and sudden transitions. And those processes have long suggested that the lightest black holes should be heavier than the most massive neutron stars. A small black hole in the gap would therefore not challenge the existence of black holes. It would challenge the story of how some of them are born. In this version, the companion had no surface during the final orbit, It didn't carry a crust, a core, or nuclear matter pressed to its last resistance. It was already defined by an event horizon, a region where every future path for light and matter leads inward. Its merger with the larger black hole would have been a clean meeting of horizons, with gravitational waves as the main outward release. That naturally explains the missing light. There would be no neutron-rich material to tear loose, no decompressed matter to build a kilonova, no exposed interior to reveal itself through color and fading heat. The darkness of the event would no longer require swallowing a neutron star whole. It would be the expected silence of two black holes in an environment with little gas. The difficulty is that such a neat final act has to be preceded by a much less neat origin. Stellar collapse is the first place to look. A massive star forms an iron core. The core collapses, and the outcome depends on whether the explosion can expel the outer layers or whether gravity keeps drawing material inward. If a neutron star forms and remains stable, the remnant stays below the collapse threshold. If too much material falls back, or if the shock fails to revive the explosion, a black hole can form. But when a black hole forms inside a dying star, it may continue to swallow nearby matter, raising its final mass. This is why a minimum of several solar masses has often seemed reasonable for black holes made directly by stellar death. The collapse does not pause just above the neutron star limit with ease. Once the horizon appears, surrounding material has a way to disappear into it. To leave behind a black hole only slightly heavier than the heaviest possible neutron star, the explosion and fallback would have to be finely balanced. Enough mass must collapse to pass the threshold, but not so much that the remnant grows into the more familiar range. Such balance may occur, but it asks for details that are difficult to make common. The star might have been stripped by a companion before death, losing much of its envelope and leaving a compact core with little material available for fallback. Binary interaction can remove hydrogen and helium layers, changing the final collapse and limiting how much mass remains to be swallowed. A successful but weak supernova might leave a black hole after partial fallback, while still ejecting enough material to keep the final mass low. In this picture, the small black hole is not born from an ordinary isolated massive star, but from a star whose life was reshaped by a companion long before the gravitational wave event. That possibility is important because GW 190814 itself was a binary. Its history likely involved close interaction, mass transfer, and survival through at least one compact object birth. A stripped star channel could naturally belong to such a setting, though it would still need to explain how the system avoided disruption and ended with such a large mass ratio. Another possibility is delayed collapse. A neutron star may be born massive but not immediately beyond the limit. Later, it can gain matter from a companion through accretion, or lose enough rotational support to become unstable. If its mass crosses the threshold, it collapses into a black hole. Such a black hole could inherit a mass close to the neutron star maximum, placing it naturally in the gap. This route makes the object small because it begins as a neutron star rather than as a direct black hole from a stellar core. It also connects the two sides of the boundary in a more intimate way. The black hole would be the afterlife of a neutron star that held for a time and then failed. However, this path comes with its own questions. The neutron star must gain or retain enough mass without collapsing earlier. The collapse may release little light if most of the mass falls inward cleanly. In a binary with a much heavier black hole, the earlier stages must still lead to a close compact pair rather than disruption before the final in-spiral. Dense stellar environments offer another route. In globular clusters, nuclear star clusters, or other crowded regions, compact objects can meet and exchange partners. A black hole in the gap might be a second-generation object, formed by the merger of two neutron stars or by the collapse of a heavy merger remnant. If two neutron stars merge and produce a black hole after ejecting some mass and radiating energy, the final remnant can fall into the low-mass black hole range. Later, through dynamical interactions, that small black hole might pair with a heavier black hole and eventually merge again. This channel would make the companion a relic of an earlier compact collision. Its small mass would not reflect the direct death of one massive star, but a history of assembly. Such a route can populate the gap without forcing ordinary supernovae to make low-mass black holes frequently. Yet it also requires a suitable environment dense enough to allow repeated encounters and time for the new binary to shrink. The object would carry a hidden past, one merger folded inside another. Primordial black holes form a more speculative possibility. These would not come from stars at all, but from high-density regions in the early universe collapsing under their own gravity. In principle, such objects could have a wide range of masses, including the boundary region. A primordial origin would avoid the constraints of stellar collapse completely. But this explanation demands caution. Primordial black holes remain hypothetical, and their abundance is strongly constrained by observations. The gravitational wave signal by itself does not carry a label saying that the object is primordial. It only shows that a compact body had a certain mass. Stellar and dynamical pathways must be examined first, because they arise from known populations of stars and remnants. Still, the possibility remains part of the wider meaning of a low-mass black hole once the mass gap is entered. Origin stories multiply. A small black hole would also change how the mass gap is interpreted statistically. If more events like this appear and most remain dark, with little sign of matter, the gap may begin to look less like a forbidden interval and more like an undercounted population. The lower edge of black holes would move downward. Supernova models would have to allow more fine-grained outcomes, or dynamical channels would have to seed the gap. The distinction between the heaviest neutron stars and the lightest black holes would become less secure if their masses overlap. Identification would require more than weighing. It would require tidal signatures, counterparts, spins, eccentricities, and population patterns. A black hole interpretation for GW 190814 weakens the habit of treating the boundary as empty space. In the black hole version of the event, the companion is simple in structure and difficult in history. It has no material interior accessible to astronomy, no surface that could deform, no crust that could break, and no equation of state to reveal. It is, from outside, almost purely gravitational, yet that simplicity forces complexity backward into its formation. Nature must make a horizon where older expectations left few examples. It must either collapse a star with unusual restraint, transform a neutron star after birth, assemble remnants in a dense environment, or reach into more speculative early universe channels. The final merger would be dark and clean, but the path to it would not be. That is the quiet reversal of the black hole interpretation. The object becomes easier to understand at the moment of collision and harder to understand before it. If GW 190814 contained a 2.6 solar mass black hole, then the boundary was crossed before the detectors ever heard the signal. Matter had already lost, perhaps in a supernova, perhaps in a delayed collapse, perhaps in an earlier merger. What arrived at the larger black hole was not a star under final pressure, but a small horizon carrying an unfinished history. The event would then say that black holes can occupy territory once left almost entirely to uncertainty, and that the lower edge of the black hole population may be shaped by channels still only partly mapped. The growing catalogue of gravitational wave events changes the boundary problem from a single puzzle into a population study. One signal can expose a strange object, but it cannot reveal whether that object is common, rare, or produced by a special accident of formation. GW 190814 placed a compact body in the mass gap and made the gap feel occupied. The next question is whether more bodies will appear there and whether they will arrive with similar companions, similar darkness, or different traces of matter. This is where gravitational wave astronomy becomes cumulative. Each merger is brief, but the catalogue remembers. It records masses, spins, distances, mass ratios, and the presence or absence of light. Over time, those measurements can turn ambiguity into pattern. The first boundary object may remain unresolved, but a population of boundary objects cannot stay formless in the same way. It will begin to show structure, and that structure will decide whether the strange companion was an outlier or the first clear member of a hidden class. The power of future detections lies partly in repetition. If many compact objects appear between the heaviest neutron stars and the familiar black hole population, then the old mass gap will no longer look like a clean absence. It may become a valley rather than an empty region, with fewer objects than on either side but enough to demand explanation. If, instead, only a handful of such events appear after many detections, the gap may remain mostly real, crossed only by rare pathways. Either outcome matters. A filled gap would ask for new or revised formation channels, perhaps involving stripped stars, delayed collapse, accretion, grown neutron stars, or dynamical assembly in dense clusters. A nearly empty gap would strengthen the idea that stellar death naturally jumps over the interval most of the time. Statistics would turn the question from whether one object can be explained into how nature distributes compact remnants across the boundary. Mass alone will not be enough. Future catalogues must also track how these objects are paired. A boundary mass companion orbiting a much heavier black hole may be difficult to classify, because the heavier object can swallow it quietly. A boundary mass object paired with another neutron star, or with a lower mass black hole, could behave differently. It might deform more visibly in the waveform. It might be torn apart outside a horizon. It might leave debris bright enough for telescopes to identify. The same mass in a different binary can give a different kind of evidence. This means the catalogue must be read not as a simple list of weights, but as a set of encounters. The nature of the companion, the mass ratio, the spin of the black hole, and the orbital geometry all influence whether the boundary object reveals itself. A future event in the same mass range with a clear kilonova would strongly suggest that at least some objects there are neutron stars. A future set of dark mergers with no tidal imprint might point towards small black holes, though even then compact neutron stars could remain hidden in some cases. Spin measurements may carry another clue. Black holes formed through ordinary stellar collapse can inherit or acquire spins shaped by the angular momentum of their progenitor stars and binary interactions. Black holes formed through previous mergers may have spin patterns influenced by the geometry of earlier collisions. Neutron stars have their own spin histories, including birth rotation, magnetic braking, and possible acceleration by accretion. In gravitational wave signals, spin is often difficult to measure precisely, especially for the lighter object, but a growing population can still reveal trends. If boundary mass objects tend to appear with spins unlike those expected for neutron stars, that would matter. If their spins cluster with known neutron star behavior, that would matter too. No single spin measurement may solve the identity of one compact body, yet many such measurements can begin to separate histories. Population science works by letting weak clues become stronger together. The environments of the mergers may also become clearer with time. Some binaries likely form through isolated stellar evolution, beginning as pairs of massive stars that exchange mass, survive supernovae, and gradually tighten. Others may form dynamically in clusters, where compact remnants meet, exchange partners, and sometimes merge repeatedly. The mass gap may be populated differently in these two settings. Isolated binaries may produce low-mass black holes through stripped stars or delayed collapse. Dense clusters may produce second-generation objects, including black holes made from earlier neutron star mergers. If future gravitational waves show eccentric orbits, unusual spin orientations, or repeated patterns of hierarchical merging, they may point toward dynamical origins. If they show aligned spins and masses consistent with shared stellar evolution, they may favor isolated channels. The boundary between neutron stars and black holes is therefore also a boundary between possible histories. The object identity is not only what it is now, but how it arrived there. Improvements in detectors will make this mapping more refined. Greater sensitivity means weaker and more distant mergers can be found, but it also means nearer events can be measured with better detail. Tidal effects that are hidden in one signal may become visible in another. Ringdowns may be clearer. Sky localization may improve when more detectors join the network, allowing telescopes to search smaller regions more quickly. Better localization increases the chance of finding electromagnetic counterparts when they exist. A faint glow that would be lost in a broad search might be recognized if the region is narrow and the response is fast. In that sense, the future of the boundary problem depends not only on hearing more ripples, but on coordinating the listening with light. Gravity can weigh the object. Light, when it appears, can reveal matter. Together they can distinguish a surface from a horizon more powerfully than either can alone. Theoretical work will have to evolve alongside the observations. Every new event in the boundary region constrains dense matter and stellar collapse at the same time. If a high-mass neutron star is confirmed, equations of state must allow it. If a low-mass black hole is confirmed, formation models must make it. If both appear in overlapping mass ranges, then the old habit of assigning identity by mass will fail. Models will need to predict not just maximum neutron star mass or minimum black hole mass, but the full distribution of compact objects and the conditions under which each type appears. That includes uncertainties in supernova engines, binary mass transfer, natal kicks, metallicity, cluster dynamics, accretion, and the behavior of matter above nuclear density. The boundary is a narrow place in mass, but it connects many fields of physics. A waveform from one merger can touch nuclear forces, stellar winds, relativistic gravity, and the demographics of ancient stars. There is also a quieter lesson in how scientific categories change. Neutron stars and black holes are not arbitrary labels. They describe genuinely different physical states, one with matter supported outside a horizon, the other with no visible surface at all. Yet observation may reveal that the transition between their populations is not a clean observational gap. The same mass could belong to either state. A heavy neutron star and a light black hole might be neighbours, or even overlap in the catalogue. This does not erase the difference between them. It makes the evidence needed to tell them apart more subtle. Categories remain useful, but they must be earned from multiple signs rather than inherited from a simple mass range. The boundary becomes less like a wall and more like a terrain, with hidden ridges shaped by formation, composition, and collapse. GW 190814 will remain important because it arrived early enough to unsettle the map. Later catalogues may explain it, absorb it, or show that it was the first of many similar detections. It may become an example of a low-mass black hole, a massive neutron star swallowed without light, or a member of a mixed population where both interpretations occur. Its meaning will depend on what follows. The event itself is over, but its category is still being written by the detections that come after it. As the catalogue grows, the boundary will be tested not once but repeatedly, from different masses, distances, partners, and environments. the question will gradually shift from what was that one object to what kind of universe makes objects there at all. In that shift, the strange companion becomes part of a larger census of compact remnants, a census conducted through the faint geometry of mergers that were dark until spacetime made them measurable. The boundary itself is not a place in space where a traveller could pause between a neutron star and a black hole. It is a condition, a threshold written into gravity, pressure, density, and time. On one side, matter still has an outward answer to collapse. It may be crushed into nuclear density, stripped of ordinary atomic form, curved by its own gravity until light struggles to escape, but it remains matter arranged outside a surface. On the other side, the surface is gone from the outside universe. The event horizon replaces it, not as a solid wall, but as a limit in space-time beyond which every future path leads inward. The strange companion in GW 190814 matters, because it sits where those two descriptions come closest together. It forces the distinction to become physical rather than verbal. The question is not whether neutron stars and black holes are different. They are. The question is how nature moves from one to the other, and whether observation can recognize the transition when the evidence is almost entirely gravitational. In simple diagrams, the categories appear clean. A neutron star occupies one region of mass and radius. A black hole occupies another. Between them, a line marks collapse. But real objects do not arrive as points in a classroom figure. They arrive with spin, thermal history, magnetic fields, binary companions, formation channels, and uncertain interiors. A neutron star may be heavier because it accreted matter over time. It may spin fast enough to delay collapse. It may contain exotic particles that soften the core, or strong interactions that stiffen it. A black hole may be light because it formed from a stripped star, from delayed collapse, or from an earlier compact merger. The mass alone becomes a starting clue rather than a final identity. Near the boundary, the old habit of naming an object by where it falls on a scale begins to fail. The universe does not guarantee that every category will remain separated for the convenience of measurement. This does not make the boundary vague in the physical sense. A neutron star has material structure outside a horizon, while a black hole does not. The difference is profound. If a pulse of light is emitted from the surface of a neutron star, it can still escape, though stretched and reddened by gravity. If light is emitted inside a black hole's horizon, it cannot reach the outside universe. If matter is torn from a neutron star before it falls in, it can glow, form heavy elements, and carry nuclear information outward. If matter crosses the horizon, its later story is hidden. The distinction remains exact for each object. What becomes difficult is access. Observation may weigh a body without revealing whether its mass is supported by dense matter or already enclosed by a horizon. The frontier is sharp in nature but blurred in evidence. GW 190814 stands inside that blur. Its smaller companion may have been a final neutron star, so compact and heavy that it approached the horizon without becoming one. Or it may have been a small black hole, already past the surface-bearing stage before the final orbit began. Both possibilities reach into different parts of physics, and neither can be dismissed without asking what else must be true. A neutron star interpretation demands strong dense matter, a high maximum mass, and a formation history that preserves such an extreme object. A black hole interpretation demands a channel that creates a horizon at a mass where older observations found few examples. In each case, the event is not isolated. It pulls on the equation of state, supernova mechanisms, binary evolution, cluster dynamics, and the selection effects that shape the earlier catalogue. The boundary becomes a meeting point where many uncertainties cross. One reason the transition is so compelling is that neutron stars and black holes both represent endings, but different kinds of endings. A neutron star is the end of ordinary stellar matter under compression, a remnant where the ashes of fusion have been forced into a new state. It is the last stable answer matter can give after a massive star's core collapses. A black hole is the end of that answer. It is not merely denser matter in the usual sense, because density inside a horizon does not describe an observable surface in the same way. From outside, the black hole is characterized by mass, spin, and charge, with almost all details of the material origin hidden. The boundary between them is therefore a boundary between memory and erasure. A neutron star preserves clues in its radius: crust, magnetic field, pulses, temperature, and tidal response. A black hole preserves far less externally. When collapse occurs, much of the interior complexity no longer remains available to distant observers. Gravitational wave astronomy has made this frontier more active because it observes the moment when compact objects test each other. A pulsar can be weighed calmly in a binary system, and an X-ray binary can reveal a dark companion through accretion. But a merger forces the issue under extreme conditions. Tides may deform a neutron star, matter may be stripped, a remnant may ring down. The waveform becomes a record of how compact bodies behave when separation disappears. Yet the same violence can also hide the answer, especially when a large black hole swallows a smaller body before material escapes. The method that brings the boundary into view can also carry the evidence beyond reach. That tension gives GW 190814 its lasting shape. It was detected because spacetime changed measurably, but the classification depended on signs that may never have had a chance to leave. The event also reminds science that categories are often built before the full population is known. For years, neutron stars and black holes were studied mostly through light and its consequences: radio beams, X-rays, companion motions, supernova remnants, and the glow of accretion. Those methods revealed real objects, but not necessarily all objects. Gravitational waves added a population selected by merger, and immediately some of its members challenged inherited expectations. The mass gap may still be partly real. It may still mark a tendency in stellar death, but it can no longer be treated as an untouched blank. At least one compact body has been weighed there, and future detections will decide whether the interval is sparsely populated, richly layered, or shared by different object types. The boundary is being mapped by events that were once completely dark. There is a deeper humility in that change. The universe did not alter its categories when the detectors turned on. The objects were already merging, already forming, already crossing or approaching the limit between pressure and horizon. What changed was the reach of observation. A ripple passing through Earth gave access to a hidden census, and the first entries in that census did not simply confirm the old picture. They made it more exact and less comfortable. This is often how scientific frontiers move. A boundary that seemed clean from a distance becomes textured when measurements improve. The question does not disappear, it gains edges. Theories that once had wide room are pressed inward by mass, spin, tidal limits, and non-detections. Speculation remains, but it is no longer free to float. It must attach itself to signals. In the end, the strange boundary between neutron stars and black holes is not only about the heaviest possible star or the lightest possible black hole. It is about the last visible form of matter and the first hidden form of collapse. It's about how much pressure the strong force can provide, how massive stars fail, how binaries survive, and how darkness can still carry measurable structure. GW 190814 did not draw the line with certainty. It placed an object directly where the line is hardest to see. That may be its most important contribution. It turned a theoretical boundary into an observed difficulty, and an observed difficulty into a guide for the next generation of detections. Somewhere near 2.6 solar masses, nature has left a marker. It may mark matter holding almost impossibly long. It may mark a horizon formed unexpectedly small. Until more signals gather around it, the marker remains unresolved, but it is no longer invisible. The boundary has been touched, and from that contact the map of compact objects has begun to change. The signal has ended, but the boundary it revealed remains open in a quieter way. A neutron star and a black hole are not variations of the same object. One still holds matter in a state of extreme resistance. The other hides its interior behind a horizon where outside observation can no longer follow. Yet near the mass where the heaviest possible star approaches the lightest possible black hole, that difference becomes difficult to read from a distance. The universe may place a surface and a horizon close together, then allow gravity to erase the evidence before light can escape. That is what makes the boundary so patient and so exacting. It is not loud. It does not announce itself with certainty every time a merger is heard. It waits inside waveforms, inside missing flashes, inside the slow accumulation of masses that do not fit the older map. GW 190814 is one such marker, a compact object weighed in the dark and left unresolved enough to keep science moving. If it was a neutron star, then matter survived closer to collapse than many models would prefer. If it was a black hole, then nature found a way to make a horizon smaller than expected. Either path leads back to the same frontier, where pressure, collapse, stellar death, and observation meet. Future detections will not remove the mystery all at once. They will soften its edges, one signal at a time, until a pattern begins to appear. Some objects may prove to be heavy stars. Others may prove to be small black holes. The boundary may become less like a gap and more like a narrow landscape, shaped by histories still being uncovered. For now, the strange companion remains a quiet weight in the catalogue, not fully named, but no longer hidden. It has shown that even darkness can carry information, and that the final difference between a star and a black hole may be measured first as a ripple passing through Earth. Long after the merger itself has gone still,